Thanks to Brilliant for sponsoring today's video.
In some previous videos, we looked at a set theoretic model of the natural numbers and their arithmetic. And today what I'd like to do is maybe extend that from the natural numbers, which correspond to finite sets, to infinite sets. And we're going to think of these as infinite ordinals, whereas we thought of the natural numbers, or will now think of the natural numbers as finite ordinals. So let's maybe recall a little bit of what we've done in the past. So we can make natural numbers in via sets by 0 is equal to the empty set. 1 is the set containing 0, which is of course the set containing the empty set. And then 2 is going to be the set containing 0 and 1, or as sets, this is the set containing the empty set and the set containing the empty set. And then, well, I think you can probably see the pattern here. N will be the set containing 1, 2, 3, 4, up to n minus 1. Okay, so good. We've got all of the natural numbers defined as sets, and also, interestingly, they're all built out of the empty set. Now what we'd like to do is define addition in this structure, and this can be done recursively. And, well, we'll first define how to add 1. And we'll think about this addition by 1 as a successor function, which we'll write as s of n. And, well, if you see what's going on here, well, this looks exactly like n union the set containing n. Well, that's n plus 1 at least. Let's make sure that makes sense. Well, what's the successor of 1? Well, notice that it's going to be 1 union the set containing 1. So that's exactly what we get here. Because here we get the elements of 1, and then this is the set containing 1. Okay, so our main question that we want to talk about today is how can we extend this to infinite sets, or in the language today, infinite ordinals? And, well, first we're going to look at something called, well, the set of all natural numbers, which we haven't talked about here. We've just talked about individual natural numbers. And in fact, the set of all natural numbers will be our first so-called limit ordinal. So exactly how would we write that? Well, like I said, it's going to be all natural numbers, but in this world of ordinals, we generally use the letter omega. So this is equal to 0, 1, 2, 3, so on and so forth. So in other words, all natural numbers. And then let's maybe note something that's very important about limit ordinals, and that is omega does not have what I'll call a precursor. So, well, what do I really mean by a precursor? Well, I mean that there does not exist another ordinal, which I'll call alpha, such that omega is equal to the successor of alpha. Okay, but then how could we define omega if it's not defined as the successor of a single ordinal? Well, let's maybe make the following second observation. And that is that, in fact, omega is equal to, well, look, it's the set containing all of the natural numbers, but we could write that as 0, union 1, union 2, union 3, union 4, union 5, and so on and so forth. Now, this may seem like a strange way to write it, but in fact, taking this union will exactly give you the set of all natural numbers, just thinking about what's going on here. So 0 is the empty set, and we're unioning that with the set containing the empty set, and then we're unioning that with the set containing the empty set and the empty set, and so on and so forth. But these are all nested inside of each other, so that's why we're going to get this set of all natural numbers. And then maybe furthermore, let's notice that this is in fact equal to the union of all ordinals lambda that are less than omega. So what do I mean by less than here? Well, less than is simply contained inside of. So now what I want to do is notice a couple of things that are true about all of the objects we've been looking at so far. That is omega, this first limit ordinal, and then all of these finite ordinals over here. So let's maybe notice this first one, and that is they are well ordered. So, well, what do I really mean by that? Well, I can put them in this like nice list. So we have 0 is less than 1, is less than 2, is less than 3, is less than 4, is less than 5, so on and so forth. And then, well, what's also true? Well, there's this kind of other rule, which I'm not sure I have a name for this other rule, but it goes something like this. So every element of omega, or n, viewed as a natural number over here, is a subset of omega, or n, for instance. So let's just look at that. So let's notice, for instance, 5 is an element of 6, which is the set containing 0, 1, 2, 3, 4, 5. But then furthermore, we have 5, which is the set containing 0, 1, 2, 3, 4, is in fact a subset of 6. So that's what's going on with this second property. So every element is a subset. So, but this isn't only true for this 5 and 6 example we've done. That's true for every element of omega as well. Okay, so how could we generalize this to like maybe a definition, or maybe abstract it to a definition is a better terminology here. So we'd say S is an ordinal, where S is just a set, if, so first of all, it's well ordered. So I'm not gonna like look at the precise definition of that. Maybe I urge you to look that up if you want to. Why we're not gonna look at the precise definition is because we're mostly looking at all of the ordinals built out of the natural numbers, or really built from the empty set, which is sort of obviously well ordered, and also it's something called the von Neumann set theory universe. Okay, so that's the one thing, and that is, and then the other thing is this weird property where every element is a subset. So if X is an element of S, then X is a subset of S. Okay, so now, well, we've at least extended these natural numbers to something a little bit bigger. Now, maybe we could think about doing some sort of arithmetic on ordinals that are non-finite, or infinite ordinals. So in other words, instead of having addition defined like this down here, which only works for these finite ordinals, could we perhaps do it for infinite ordinals? So let's get to that setup.
Hey there, I'd like to take a minute to talk about today's sponsor, Brilliant.org. While watching my videos is a great place to start, you get more out of learning by doing. And that's why I highly recommend you sharpen your skills with Brilliant. Brilliant is where you learn by doing, with thousands of interactive lessons in math, data analysis, programming, and AI that are individually matched to your unique level. Each lesson comes with hands-on problems so that you can truly learn the material. It's been proven to help you learn 6 times more effectively than just watching videos. Content is designed by an award-winning team from MIT, Caltech, Duke, Microsoft, Google, and more. You'll find yourself learning real-life problem-solving skills instead of memorizing equations. Brilliant can replace mindless doom scrolling on your phone, since it can be easily incorporated into your daily activities with fun lessons you can do on your phone, or on your tablet, or on your computer, all in just minutes a day. Check out their course library. They have new lessons on scientific thinking that will have you comparing circuits to understand voltage and current, playing snooker to learn the rules of collision, planning your itinerary for an intergalactic music festival on a space-time diagram, and more. It's perfect for learners of any level. But we're scientists here, so don't take my word for it. You should test it for yourself. Treat yourself to a unique hands-on experience by going to brilliant.org/MichaelPenn for a 30-day free trial and 20% off your annual subscription. Thanks once again to Brilliant for sponsoring today's video.
Now we're ready to dip our toes into the arithmetic of infinite ordinals. So we define addition, well, and multiplication via something called transfinite recursion. And well, what that means is, well, not only do we have to talk about what's happening for the next object, which would be normal recursion, defining the next object in terms of previous objects, we need to define how something works if there is no previous object, which would be if you're in some sort of limit ordinal situation in this case. Okay, so let's say that alpha and beta are ordinals, and well, let's just assume they're arising from the empty set. So at the moment, the only ones that we can really get our hands on are the natural numbers, well, and omega, the set of all natural numbers. But via this addition and the multiplication that we'll see a bit later, we'll be able to get our hands on larger ordinals. Okay, so we'll first say that alpha plus 0 is equal to alpha. Okay, so that's sort of obvious. And then we'll say that alpha plus the successor of beta is the successor of alpha plus beta. Notice that this is exactly what happened in the finite case. But in the finite case, everything, well, except 0 or the empty set had a precursor, so this kind of definition always worked because something was always the successor of something else, except, like I said, 0. But in the infinite case, that isn't the case anymore. In fact, we have to look at what happens if we have a limit ordinal, like omega, for instance. That's the only one we know so far. So if beta is a limit ordinal, we'll define alpha plus beta to be the union over all lambda less than beta of alpha plus lambda. Okay, so let's look at a couple of examples. So let's start with omega plus 1. Okay, well, omega plus 1, 1 is not, well, it's not 0. It's not a limit ordinal, but it is the successor of something. It's the successor of 0. So this is omega plus the successor of 0. Okay, but that means here we're going to get the successor of omega plus 0. In other words, we're going to get the successor of omega. But recall how we defined the successor before in the finite case. That's exactly how we're going to define it again. So this is equal to omega union with the set containing omega. Okay, so, well, what does that really look like? Well, that's going to look like, well, omega contains 1, 2, 3, 4, so on and so forth, and that never ends. But at the end, we'll get, well, this thing right here, omega itself. Or if we were to write this out, we would have 1, 2, 3, 4, all the way up, and then at the end, we would have the set containing 1, 2, 3, 4, and then that never ends as well. And you might say, well, maybe you should just put this omega at the beginning, or this set of all natural numbers at the beginning, so it doesn't like trail off and we've got infinitely many things before we hit omega. But this is maybe the standard way to list everything inside of this set, which is omega plus 1. And that's because it gives some sort of ordering to it. Observe that omega plus 1 has this nice ordering. 1 is less than 2, is less than 3, is less than 4. And then all of the natural numbers are less than omega. Okay, well, let's see what happens if we were to do 1 plus omega. Instead of omega plus 1, I guess I should point out that we're obviously checking here if it's commutative, and well, we wouldn't be checking it if it's commutative unless something surprising happened. So let's see. Omega is a limit ordinal, so this is equal to the union over all lambda less than omega of 1 plus lambda. But that's equal to the union over all natural numbers of 1 plus that natural number, just given the things inside of omega and the things that are less than omega. But now addition of natural numbers, which is what we're in right here, is indeed commutative. So we might as well swap those around, and we have the union over all natural numbers of n plus 1. Oh, but then let's observe that that's simply 1, union 2, union 3, union 4, so on and so forth. But let's also notice that 0 is equal to the empty set, so we might as well just union 0 at the beginning. But now, by our previous discussion, we noticed that this was in fact equal to omega itself. So here we've got that is equal to omega, because if you just write out the sets like we did before, you'll see that you get the set containing all natural numbers. So the interesting thing here is if we left add by the number 1, nothing really happens. Whereas if we right add by the number 1, we definitely get something that is, in some sense bigger. Let's also make the following remark, and this remark is like easily proven, maybe with inductive argument, or you probably don't even need induction, and that is for all natural numbers n, you can check that n plus omega is indeed equal to omega. Let's see what happens if you add omega to itself. So in other words, we have limit ordinals in both of these entries. Okay, so let's see what omega plus omega is. So omega plus omega, so that's going to be, let's see, the union over all lambda, which are less than omega, of omega plus lambda, because omega is a limit ordinal. But then since omega is the set of all natural numbers, that's the union over all natural numbers of omega plus n. Okay, but then that's indeed equal to omega plus 0, which is omega, union omega plus 1, union omega plus 2, union omega plus 3, and so on and so forth. Now, let's recall that these are all nested inside each other. So omega, well, that's going to be the set of all natural numbers. So we have 0, 1, 2, 3, so on and so forth. And then remember, omega plus 1 was the set of all natural numbers. And then, well, omega at the end. And then omega plus 2 is going to be kind of similar to that. So that's going to be the set of all natural numbers, and then omega and omega plus 1 at the end. So I think you can see what's going on here. We're getting this other copy of the natural numbers living above, well, the standard natural numbers. So if you were to write this out, maybe as well as we can, you would have something like this. You would have this first set of natural numbers, so 1, 2, 3, 4, so on and so forth. Obviously, that doesn't end. But above that, larger than that, you would have omega. And then just above that, you would have omega plus 1, omega plus 2, omega plus 3, and then that would continue on and on and on. So this omega plus omega is truly two copies of the natural numbers. You could think about this as our first copy of the natural numbers. Maybe we'll just call them blue natural numbers. And then maybe this second is this magenta natural numbers. So perhaps you could write this as a list of elements like this. We have 0, 1, 2, 3, so on and so forth. And then above that, we have another copy of 0, 1, 2, 3, so on and so forth, where all of the magenta colored numbers are larger than all of the blue colored numbers. And in fact, maybe we have kind of an obvious ordering, given by the listing that we have made in the set above. So it would maybe look something like this if you were psyched to write it out as an inequality. The important thing to remember here is there are infinitely many objects between, well, this number 3 and then magenta 0. Okay, so now I think, well, we've got some sort of idea of how this addition works in general. Now let's jump and look at multiplication. Let's look at how multiplication could be defined for more general ordinals. Again, we've got alpha and beta are ordinals, and they're still in that universe built from the empty set. So we'll define these again via transfinite recursion, where alpha times 0 is equal to 0, and then alpha times the successor of beta is alpha beta plus alpha. So the way you want to think about this, just to make sure that this is the right way to define it, is notice that alpha times beta plus 1 is alpha beta plus 1. That looks like the distributive rule, so that's kind of what's going on here. And then if you have a limit ordinal, then alpha times beta is equal to the union over all lambda less than beta of alpha times lambda. Okay, so let's do a couple of examples. So let's see what we get if we multiply on the right by a natural number. So let's say that alpha is any ordinal at this moment. So alpha times 1, well, that's equal to alpha times the successor of 0, which is alpha times 0 plus alpha. That's equal to alpha. So that's good because, well, we should expect multiplying by 1 is like an identity type operation. Then let's look at alpha times 2. So that's going to be alpha times the successor of 1, or alpha plus alpha. Okay, great. So that makes sense as well. Alpha times 2 should be alpha plus alpha. That kind of makes sense. And then let's specialize this to our limit ordinal omega and observe that omega times 2 is going to be equal to omega times the successor of 1. I guess I'm just repeating this, which is omega plus omega. But then recall that that was our nice kind of double copy of the natural numbers, one copy right after the other. Okay, good. Now, what happens if we left multiply by a natural number? So let's perhaps start with 1 times, and let's make sure that we're working with a limit ordinal here. And since it's the most simple to work with omega, let's work with that. So 1 times omega, so that's going to be equal to the union over all n in natural numbers, just specializing this to the case of omega, of 1 times n. Okay, so that's going to be equal to the union over all natural numbers of, well, the natural number n. But let's write this out. So that's going to be the union over all natural numbers of the set containing 0, 1, 2 up to n minus 1, keeping in mind the set definition of n. But now if we union all the sets like that, we're clearly going to get all natural numbers, so we're going to get the set omega. Okay, so that's good. It looks like left multiplication by 1 is also an identity operation. So it looks like the number 1 is a true identity from the left and from the right. So now let's look at 2 times omega and see if we get the same thing as omega times 2. Okay, so this is going to be the union over all natural numbers of 2 times n. But now that's going to be equal to the union over all natural numbers of 2n. But that's the set containing 0, 1, 2, all the way up to 2n minus 1. Just, again, keeping in mind the set definition of 2n. But then if you union all of those sets, you're going to get omega again. So left multiplying by 2 is like an identity operation. And you can probably see that this will generalize to maybe left multiplying by any natural number doesn't have an effect. So in other words, for all natural numbers n, we have n times omega is in fact equal to omega. Now let's maybe look at what omega times omega is. Okay, so maybe to finish off the examples for this video, before I kind of leave you with a question, let's look at, like I said before, omega times omega. So since that's a limit ordinal, that's going to be the union over all natural numbers n of omega times n. So here we have omega times 1, or I guess I should say omega times 0, union omega times 1, union omega times 2, union omega times 3, and so on and so forth. So let's write each of these out. So omega times 0 is 0. Omega is, well, the set containing all natural numbers. So that's that. Let's maybe color code this so we can see where all of these are coming from. And then we're unioning that with omega times 2, which let's recall that that was omega plus omega, which was that nice double copy of the natural numbers. So this was the set containing 1, 2, 3, all the way up, and then we had omega, omega plus 1, and then so on and so forth. Okay, so that is this. And then what's omega plus 3, or times 3, I should say? So by the second dot, you'll see that that's going to be omega times 2 plus omega. So, well, what does that mean? Well, that's going to give us 3 copies of the natural numbers. So perhaps we would write this as union. So we have 1, 2, so on and so forth. Then we have omega, omega plus 1, so on and so forth. And then at the top of that, we'll have omega plus omega, and then omega plus 1, and so on and so forth. So those are our 3 copies of natural numbers. But now this limit, or this union, is infinite. So in fact, if you total all of this up, what we'll have is omega copies of natural numbers, maybe one after each other. So perhaps we could write it like this. So let's maybe write the normal natural numbers, 1, 2, 3, so on and so forth. But then instead of writing omega, omega plus 1, let's maybe subscript these a little bit. So this would be our 0th copy of natural numbers. So 1 sub 0, 2 sub 0, 3 sub 0, so on and so forth. Then we have 1, 1, 2, 1, 3, 1, that continues. Then we have 1, 2, 2, 2, 3, 2, that continues on. And then we'll have 1, 3, 2, 3, 3, 3, that continues on. And then we keep going on and on and on. So what we have is, well, it's something like ordered pairs of n cross n. So natural numbers cross natural numbers. But what we've done is we've put them in this total ordering, just like linear ordering. Okay, so maybe there's an obvious question above all of this. And the obvious question is, well, first of all, what about exponentiation? So we haven't done all of the arithmetic operations. But other than that, when do we get uncountable ordinals? Like, has there been an uncountable ordinal on the board yet? Well, in fact, there hasn't. This is the largest ordinal we've seen, but this is the size of natural numbers cross natural numbers, which is countable. So I think maybe we'll save exponentiation and the topic of the first uncountable ordinal for a future video, and that's a good place to stop.